home. In this video, we're going to be discussing the 9-point circle, which is a really cool construction that applies to any triangle. We're going to discover and prove the basic features of the circle, and we're going to identify the points that are known to pass through the circumference of the circle. So let me remind you of this figure. There's a lot going on in this very complicated figure, so I want to remind you what's going on. This figure is taken from our Euler Line figure, and we're going to use it and extend our knowledge about it. But let me remind you what's going on here. We have a triangle ABC. In blue here, also called cerulean, we've sketched everything that has to do with the circumcenter and circumcircle of this triangle ABC. So the perpendicular bisectors of its segments here in blue and in blue and in blue, their intersection point, which is the circumcenter O of the triangle, and the circumscribing circle, which we won't be using, but it's nice to have it in the picture. In orange here, we have the orthocenter and its construction. It's the intersection of the altitudes. So we have the three in orange altitudes of this triangle and the orthocenter labeled H. And in mint, we have everything involving the midpoints and the median here. So we have this median AJ, this median BK, this median CL, the point of intersection, which is the centroid. We also have the midpoints J, K, and L highlighted also in green, and the triangle that connects them, which is called the medial triangle, also represented there. I want to remind you, we know a lot about the medial triangle. We know that it divides the triangle ABC into four triangles, each of them congruent to each other, and each of them similar to the original triangle ABC. We also know, furthermore, that the sides of the medial triangle are parallel to the sides of the original triangle. This side here is parallel to this one, and we've used that fact in order to prove the basic features of the Euler line. Here I've sketched the Euler line here. It's represented as the segment HGO. All three of these points are collinear, and what we know about the Euler line is that they lie in a certain ratio. Well, first of all, they are collinear. Second, the centroid lies between the other two. And finally, the centroid is slightly closer to the circumcenter. It's 1/3 of the way from the circumcenter to the orthocenter. So in other words, the segment OG is half as long as GH. So all of these things we've proven about this. Now, what we haven't dug into quite yet in relation to this figure is how these various centers relate to the medial triangle itself. And that's kind of an interesting story. So I want to point out some of these features first. First of all, the blue. The blue lines are the perpendicular bisectors of the original triangle ABC, but in relation to the green triangle or mint triangle here, the medial triangle, they are not perpendicular bisectors, right? This blue line here is certainly not, well, it is perpendicular to LK, but it certainly isn't a bisector of LK. Instead, it's an altitude. And so this line is an altitude as well. This line here is an altitude of this green triangle, and that makes O have a dual role. O is simultaneously the circumcenter of the original triangle ABC, but also it is the orthocenter of the green medial triangle. So this is also an orthocenter of something, even though it's labeled O, circumcenter. In relation to the original triangle, it's also the orthocenter of something, namely this green medial triangle. What about the centroid? Is the centroid something in relation to the medial triangle? Well, it actually looks like it might be the centroid of the medial triangle as well. In order to prove that, we need to establish whether the original green lines here, AJ for example, which are the medians of the original triangle ABC, we need to establish that those are also medians of the medial triangle JKL. What does that mean? That means that the line AJ should bisect the segment LK, and similarly around the other sides. So is this true? Well, it is true. Let's have a quick look at some important triangles here so that we can identify why this is true. So let's look at, there must be some intersection point P of the median AJ and the side of the medial triangle LK here. I said AJ. So AJ and LK here. There must be some intersection point. We can call it P. Now, what do we know about these two triangles that I've identified in gray here? Well, we know that they're similar. That's easy. Having already established that AB is parallel to JK, we have transversal across those two parallel lines, another transversal across those two parallel lines. That gives us equal angles here, and this is just an intersection of two lines, so we get vertical angles, equal angles here. So that gives us lots of angle inequalities among these triangles, and so we can say that they are similar. Are they in fact congruent? Well, when we studied the medial triangle, we identified that the length JK was exactly half of the length AB. And since L is, by definition, the midpoint of AB, then the length AL must exactly agree with the length JK. So we know the angle equalities, but we also know that JK is equal to AL in length. And that means that these two triangles are not only similar, they're congruent. So if they're congruent, then in what sense here? JKP is congruent to ALP. Which sides correspond? JK corresponds to AL. LP corresponds to PK. If so, that means that the length LP and the length PK must agree. And that, finally, means that the point P is the midpoint of the segment LK. Why do I care? Because if P is the midpoint of the segment LK, then indeed the median AJ of the original triangle is also a median of the medial triangle JKL here, because it passes through the midpoint of passes from the vertex J to the midpoint of the opposite side of the medial triangle here represented in green. So that reassures us that that this green median of the original triangle AJ is also a median of the medial triangle JKL. And the same is true for the other medians, of course. And that means that G, the centroid of ABC, is correctly labeled in relation to JKL as well. G is the centroid of JKL as well. So, this, to remind you, O is the circumcenter of ABC, but the orthocenter of JKL. G is the centroid of ABC, and also, likewise, the centroid of JKL. Now, what about, so that's, now we've accounted for the orthocenter of the medial triangle and the centroid of the medial triangle. What about the circumcenter of the medial triangle? Well, if we believe what we know from the Euler line, then we can predict where it must be. And I'm going to claim that it's here, actually halfway between H and O. So what do we know? So I'm going to label this point N, and then I'm going to explain why this point, why the circumcenter of the medial triangle needs to lie exactly here. And so what do I mean by exactly here? I mean in the midpoint between H and O. Well, we know that the orthocenter of the medial triangle and the centroid of the medial triangle and the circumcenter of the medial triangle, wherever it may be, we know that they must lie on a line. Why? Because the Euler line insight that we had as it applies to ABC must also apply to the medial triangle JKL. So we know that these 3 points in relation to JKL, namely the orthocenter, the centroid, and the circumcenter of JKL, must lie on a line in that order. We furthermore know that the centroid of JKL is between the other two, and that the distance from the centroid to the circumcenter of JKL is exactly half of the distance between the centroid and the orthocenter of JKL. In other words, everything we know about the relation H, G, and O as it applies to ABC, we also know about the relationship of O, G, and N, the circumcenter of the medial triangle, as it applies to the triangle JKL. And that means that N can only be here. It must be on this Euler line, the same Euler line as applies to ABC. It must be on that same line. And this distance has to be exactly half of this distance. So if this is 1/3 of the total distance from H to O, and this is half again as far, that's 1/3 plus 1/6, and that's halfway from O to H. That's where the circumcenter of JKL must lie. And just to verify that, let's actually produce the circle here, right? So notice I'm producing the circle through K, one of the points on the edges of one of the points on the vertices of that medial triangle and centered at N, producing that circle. And sure enough, it passes through K, J, and L. So I'm going to leave that circle there. Now, okay, I suppose if this were a theorem, it would be called the three-point circle. It's not very impressive. I've simply constructed the circumcircle of a triangle and identified that the points, the vertices of that triangle lie on that center. But there's a lot going on with the Euler line in this picture, and there's a lot more that we can say. So what I want to do next is I want to start to identify some other kind of interesting points that also lie on this purple circle. So I'm actually going to hide the circle because I don't want to confuse you about how the points are constructed. When I construct the points, I want it to be a theorem that they lie on the circle, and it will be hard to see that something is really happening if the circle is there waiting. So what I'm going to do is I'm going to construct the line connecting J to N. Okay, so this is actually a radius, at least the segment JN is a radius of that circumcircle of JKL. And I'm going to construct that radius, and then I'm going to continue it for a while. So I'm going to construct that line, and then I'm going to continue it. And I'm just going to continue it until I hit this line AH. Wherever this line of JN extended hits AH, then I'm going to label that point M. Now at this point, we have a couple of triangles that pop out. At least if I highlight them, they will. Let's look at the triangle JON and the triangle HMN. Now, these triangles certainly look congruent. Is there an easy proof that they're congruent? Well, we know some things, and there are some things we don't know about these triangles. So let's look carefully. We know that N is the midpoint of HO. And so we know that ON and HN are congruent to each other. Do we have any angle equalities? We have angle equalities all over the place. We know that this is a straight line. We know that this is a straight line. That gives us a vertical angle equality here. We've already proven that this line in blue and this line in orange are both perpendicular to BC and so parallel to one another. That means that this angle at O and this angle at H are congruent because they're alternate interior across a transversal cutting two parallel lines. And we know that this angle here at M and this angle here at J are congruent for exactly the same reason. So we get angle equalities everywhere and one length equality. So by the angle side angle criterion, these triangles are congruent. And that tells us two important things here. First of all, it tells us that OJ and HM are equal in length. That's already interesting. It also tells us that JN and NM are equal in length. The reason that's interesting is that JN is already known to be a radius of that important circle that I hid, right? So there is this important circle, and so once we know that JNM forms a straight line and JN and NM are equal in length, that proves that M is also on that circle, as it appears to be, of course. But we've just proven that it must be because we have a straight line and we verified that this length matches this length. So MJ, in other words, is exactly one diameter. Now let's return to the other equality that we've identified here, the equality between OJ and HM. Is there, does this mean anything to us? Is there anything that we can get from this? Well, actually, yes, because let's get rid of these triangles and bring in some others. We have already demonstrated in the Euler line argument that these two triangles in red are similar to each other with a length ratio of 2:1. And notice that the one on the right has OJ in it, and the one on the left has not HM, but HA in it. So we've already analyzed the relationship between these two triangles in red in the Euler line video, and they have a 2:1 ratio. That means that OJ is exactly half as long as HA. But wait a minute, we just established that OJ and HM are equal in length, and that means that there's something special about M. In particular, M is the midpoint of the segment HA. So that becomes a special feature of M. M is the midpoint of AH. And it's also one of the points on this peculiar circle in purple here, the circumcircle of the medial triangle. So what we've shown so far is that the circumcircle of the medial triangle passes through, of course, the three vertices of the medial triangle, but also the midpoint of the segment connecting the vertices of the original triangle to its orthocenter. Now here I've illustrated this for AH, but of course the same thing goes for BH, and you can see the midpoint here on the circle. And for the, in this picture very long, CH, right? This altitude in orange, if you connect C to H and then find the midpoint of that connection, you'll get this point. So the midpoints of the connectors from the vertices of ABC to its orthocenter, they likewise lie on this special circle here. But there's one more point in this picture which quite obviously lies on that circle, or seems to, and warrants some explanation, and that's the point Q. What is Q? Q is called the foot of the altitude, the bottom part of the altitude, or more precisely, where the altitude meets the side of the triangle. In this picture, Q also appears to lie on this key circle. Why? Well, it's actually a trivial consequence of everything that we've done so far. We know that this orange line and this black line make a right angle at Q, yeah? Well, we also know that MJ in this picture is a diameter of the circle. So if a right triangle is formed so that the diameter, so that its hypotenuse is the diameter of a circle, then its angle must lie on that circle, right? So, so in fact, every point along the circle here will form a right triangle with a hypotenuse mj. So this is basically a simple consequence of the inscribed angle theorem. So the any right triangle whose hypotenuse is given as the diameter of a circle will have the third vertex on that circle, and so Q itself will be on the circle. And the same, of course, goes for the feet of the other altitudes, which are here in this picture and here in this picture. And so finally, we've reached our 9 points, and it's time to put some vocabulary to this. N, this key point, which is originally defined either as the midpoint of HO or as more simply the circumcenter of the medial triangle. This point N is called the 9-point center. And the circle, which is in fact the circumcircle of the medial triangle, is called the 9-point circle because it has 3 triples of interesting points that lie on it. In particular, the vertices of the medial triangle, which are also, of course, the midpoints of the original triangle. The vertices of the medial triangle lie on the 9-point circle. The halfway points between the original vertices of ABC and its own orthocenter, those halfway points also lie on the 9-point circle. And the feet of the altitudes of the original triangle ABC, they also lie on the 9-point circle. So those are the 9 points on the 9-point circle. They are not always 9 distinct points. If you change the diagram so that you introduce, particularly if you introduce symmetries to the figure, make the circle isosceles, for example, some of these points can become the same point. But these 9 points are always concyclic. They always lie on a circle together, and that is the 9-point circle.